Hello, this is homework 3 part A, and we're going to be deriving the transfer function for a single gravity drain tank by linearizing the dynamical equation relating liquid level to inlet and outlet flows, and subtracting the steady solution and taking the Laplace transform of the deviation variables, and we're going to find out what the gain and time constant for the resulting first order our transfer function is. So what we're going to start with is we're going to go ahead and write down our equation for our gravity drain tanks, which is the area times the change in height over the change in time, which equals our Q in minus Q out, which we have seen before. So we can go ahead and just make this our equation, which is Q in minus alpha times our square root of height. And if we remember from earlier homeworks, we had our alpha, which equaled our square root of 2 times g. And from here, what we want to do is we can't take our Laplace transform just yet, as our height here we have to make into a function, since a Laplace transform can be taken unless it's linear. So a way to visualize this is if we have our graph right here, we draw our curve, which represents our square root of height, and we're going to take a point on this curve. I know it's a little terribly drawn, but we're going to have r h bar here, and we're going to have h. And if we're moving in this direction, we want to take the slope at the point right here. So we're going to go ahead and define this as h minus h bar. And we're going to write down our equation for this. So what we're going to do here is we're going to take our h to the negative 1/2 plus our dh to the 1/2 over dh. We're going to take that where h is equal to h bar, and we're going to multiply by our difference. Okay, so now what we're going to do is we're going to take our h bar, which we're going to set as 4, and we're going to go ahead and linearize our h to the 1/2, as this will help us form an equation that is a lot more linear, or it is linear, whereas this would be messy. So we're going to make our h to the 1/2 2, and if our h bar is 4, we're going to end up with 2 plus 1 over 4 times h minus 4. So this actually helps us convert that square root function to a more linear function, and now we're able to actually solve our Laplace transform. So what we're going to do next is we're going to rewrite our equation. However, since we are at steady state, our left side of the equation will be 0. So we can rewrite it as q in minus alpha times our h to the 1/2. Okay, so now what we're going to do is we're going to apply our deviation variables. And basically what this is saying is we're going to take our h prime, and that's just h minus our h bar, which we have up here, and we're just going to apply this same concept throughout. So we're going to apply our deviation variables as we're going to make our area times our dH prime over dt. And this will equal our Q in prime. And we're just going to do kind of the same thing where we have our alpha times our -1/2 plus dH half over dH, or H equals H bar. And multiply this by our H prime minus H to the 1/2. I could just go ahead and cancel this out. We're left with Q in minus times dH equals thing times H prime. And essentially this entire section here is a value, so we're going to just make that equal to R, and we're going to go ahead and make our Laplace transform. So we're going to solve using Laplace transform, and essentially what we could do is we're going to make our little s times h minus our h prime at times 0, which equals our big Q in minus our R times big H. And this is the equation that we get based off Laplace transforms. And since this is at times 0, we're going to make that 0. So what we're left with is ASH equals Q in minus RH. And what we're looking for is our Q in. So we end up with an equation based off Laplace transform that is linear rather than square root based. And this is our algebraic function that we're going to use to solve. So now what our next objective, as you could say, is now what we want to do is want to isolate our h. So what we do is what we'll get after solving that is AS plus R times R Q in, and this is our transfer function. We could visualize our system is we'll have our area right there. It's going through. We're going to have our little h and our Laplace transform, and we're going to have our Laplace transform of Q. We're going to have our Q in, and this basically just shows our system. And basically what we can do is now our height will equal our transfer function, and we find that our big Q will equal 1 over S from our system. And if we keep solving this, our H will equal K over tau times S plus R, where our K is our gain and our tau S plus R is our time constant, which is exactly what our problem statement wanted us to figure out, of what is the gain and time constant for our transfer function. And that is right here. So we've effectively taken our nonlinear function using Laplace transform to make it linear, and then we found our gain and time constant.
Actually, one thing I did on here, this is actually tau s plus 1.